Welcome back from the break. I hope you've enjoyed the break and I hope you are refreshed and alert for what's to follow. Before the break, we've been looking at titrations and we've been looking at a few of the terminology of titrations. We are going to go on now and look at proteolytic reactions. Now, we spoke about proteolytic reactions at an earlier stage. Proteolytic comes from the word proton, and that basically means it's the transfer of proton from the acid to the base. So a proteolytic reaction is the same as an acid-base reaction. Then we're also going to use the words conjugate acid-base pairs. So we will talk about a conjugate acid and a conjugate base, but let's lead on to that. Right, proteolytic reactions, as I said, it's the same as acid-base reactions. And in an acid-base reaction, we've got a proton transfer from the acid to the base, because according to the Lorentz-Bronsted theory, we know that a proton is that an acid is a proton donor and a base is a proton acceptor. So just to remind you again, this acid-base reaction is the same as talking about neutralization reaction. So when we look at hydrochloric acid will then be the acid here. And because we're reacting it with water and hydrochloric acid is an acid, it simply means that water is our base here. So we also know, except for the fact that we know that hydrochloric acid is an acid and water is a base, we also know that hydrochloric is a strong acid, which means at equilibrium, the equilibrium will lie to the right. More products will be formed because hydrochloric acid is a strong acid. So in the forward reaction, we can see that hydrochloric acid will donate a proton to the base, and the base will now take on the proton, which is now the hydronium ion concentration. So because hydrochloric acid transfer or give the proton, it's the acid, and because water accepts the proton, water is then the base. So in the reverse reaction, if we look at the reverse reaction, the hydronium ion will then in the reverse reaction give the proton to chlorine or to the chloride ion. So when hydronium ion donate the proton, it makes the hydronium ion an acid in the reverse reaction. And because chloride accepts the proton, it makes your chloride ion your base in your reverse reaction. Right, so when we have an acid and a base that forms an acid and a base, we talk about conjugate acid-base pairs. Now, a conjugate acid-base pair is normally the difference between an acid and its conjugate base is normally a proton difference. So between your acid and your conjugate base of that acid, there is a proton short because that acid has given away that proton to become the chloride ion, and that chloride ion is seen to be a conjugate base. When we look at water, and we know that because hydrochloric acid is the acid, that means that water is the base. So if you look at the base accepts the proton, making it a hydronium ion, and that hydronium ion is now the conjugate acid to water. So in a conjugate acid-base pair, the substances differ from each other by one hydrogen ion, or we call a hydrogen ion, we call it a proton. So if we look at this hydrogen chloride and water to form hydronium ion and chloride ions in our forward reaction, we know for the forward reaction, the hydrochloric acid is the acid, the water is the base, and when hydrochloric acid, as I said before, donated that hydrogen ion, it actually has one hydrogen ion less than before. So that becomes the conjugate base of the acid. If you now look at your reverse reaction and your chloride ion is now your base and your hydronium ion is now your acid, for your reverse reaction, you need to see the following. If your hydronium ion is the acid, what do we know according to Laurie and Bronsted? An acid will donate a proton and a base will accept a proton. So, if hydronium ion now donate the proton, it makes it, as we know, the acid, and the chloride ion will now be the base, and when it accepts that hydrogen ion, it becomes hydrogen chloride. So for both your forward and your reverse reaction, you should be able to see the difference of a proton between an acid and a conjugate base, or between a base and a conjugate acid. But back to the one on the board, we said that the second pair of conjugate acid base is the water is now the base in the forward reaction, and the water will now receive or accept a proton and becomes hydronium ion, and that hydronium ion in my forward reaction is the conjugate acid for water. But when it's the reverse reaction, that conjugate acid will now again transfer the proton to the chloride ion. Right, when we look at ammonium, NH3, if we mix or we react NH3 with water, we know that ammonium is a base. But we also know that water, in this case, because ammonium is the base, water in this case will now become the acid. Now in my forward reaction, once again, ammonium will then now, because it's a base, it will accept the proton. Okay? And the water, because water is the acid, water will now in my forward reaction donate the proton. So when water donates the proton in the forward reaction, it becomes OH minus, which is my hydroxide ions, meaning that if water was an acid, this is the conjugate base of the acid in the forward reaction. Sorry, the conjugate base of that acid. And what will happen now? The ammonium that will accept the proton will now become the conjugate acid of the base. So our first pair there is water and hydroxide ions, and my second pair there is ammonium, which is the base, and it becomes the ammonium ion as the conjugate acid. Right, when we look at a strong acid, when we have a strong acid, the conjugate base of the acid, remember, differs by one proton. And that conjugate acid, the strong acid will form a weak conjugate base. So this base that form here is a weak conjugate base. But when we look at the water, which is in this case a weak base, this weak base here will form a strong conjugate acid. And the strong conjugate acid to the likes of hydronium ion is now a hydrogen ion or a proton difference from the water. So when we look at ammonia, at hydrochloric acid is a strong acid. A strong acid will always form a weak conjugate base. When we look at a weak acid, when we start with a weak acid to the likes of ethanoic acid or acetic acid, it will obviously form a strong conjugate base. So if you look at your vinegar or your ethanoic acid will be an acid. Your acid will react with a base. But what will happen here is when your acid transfers the proton to the base, it will become your acetate ion. And this acetate ion here will actually be, because this is a weak acid, the acetate ion becomes a strong conjugate base of the weak acid. The same with water. Water we know, because water is an ampholyte, we know that water is not a strong acid or a strong base, because it all depends on the reaction as to how it will react. So your water will be a weak base, and this weak base will now form hydronium ions, and we know that hydronium ions will now be a strong conjugate acid for the weak base. So it's always the case that a strong acid will form a weak conjugate base, and whenever something is weak, it will form a strong conjugate acid or base. When we look at the strong base, it will form, as we know, a weak conjugate acid. And if we look at sodium hydroxide, which is a strong base, if we have this strong base to react with an acid, then the strong base will now receive a hydrogen or a proton, hydrogen ion or a proton, making water my weak conjugate acid for this reaction, and my sodium chloride coming from hydrogen that's actually given away, that my sodium chloride, my water and my sodium hydroxide, strong base, weak conjugate acid. When we look at a weak base, it will form a strong conjugate acid, the NH3, H2, and then we will have ammonium, which is a strong conjugate acid, and we have OH minus, which is a strong conjugate base. And this brings us to the wonderful part of the session. It's time for us to take a break. Go well, and I see you after the break.